So we're going to pick up where we left on section 10.2. 10.2, we were doing some calculus with parametric equations. We did example 1 last time where we were finding an equation of the tangent line. Can someone remind me how you find dy dx when you have parametric equations?
dy over dt times dt over dx.
You're close, except dot times.
Oh, divided by.
Right, that's what you meant, right?
Yeah.
dy dt divided by dx dt. So you take the derivative of your y function over the derivative of your x function. Remember that? That was a couple days ago. So we have these equations in example 2, and the question says, determine where this curve will have horizontal and vertical tangents. Where it might have horizontal tangents and where it might have vertical tangents. And they say tangents plural because we don't know how many tangent lines they might have based on what the curve looks like. They could have more than one tangent line in any direction. We saw that with that last example. So horizontal tangents. That's a little review question from Calc 1 also. What does it mean if you have a horizontal tangent line?
Means it's horizontal?
Horizontal, yeah. So what does that mean though in terms of the
Slope
function?
is zero.
The slope is 0, right? If it's a horizontal line, the slope is 0. And how do we get the slope of the tangent line?
Derivative?
The derivative. Right? So this is saying that dy dx must be 0 if it's got a horizontal tangent. The slope is 0. Let's do that one first. Let's find where the tangent line actually has a slope of 0. What do you think I should do first? Take the derivative. Thank you. Oh my, the silence is deafening right now. Take the derivative, right? If we want the derivative to be 0, we better find the derivative. It's calculus. The answer is almost always derivative or integral, right? One or the other. So let's find dy dx for this problem. The derivative of y is 6t. I did dy dt on top. The derivative of x with respect to t is 3t squared minus 3. That's the slope of my tangent line if I know what t is. All right there. So what do I want to do with that? Found the derivative. Set it equal to 0. We want the derivative to equal 0. So we want to solve 6t over 3t cubed minus 3 equals 0.
T is equal to 0.
Sorry?
And t is equal to 0.
T equals 0. The only time a fraction equals 0 is if the numerator is 0. You can see that easily by multiplying both sides by this. Yes, sir?
Plus 3t squared.
Oh, thank you. 3t squared minus 3. Thank you. So the only time a fraction could equal 0 would be if the numerator. Yes, sir?
So don't whenever we're like solving for horizontal tangents, we just want to solve for d when dy over dt is equal to 0.
Exactly. So what he's saying is that all you really need to solve is dy dt equals 0 because the numerator has to be 0. So a horizontal tangent, you really only have to look at dy dt. That's the only time that this will equal 0. So I need 6t to equal 0, so t equals 0. Now the question said, determine where the following curve will have horizontal and vertical tangents. Is this an answer to where?
Plug in 0 for x and y.
Aha, plug in 0 to find your x and your y so you actually find the point where this occurs. So this isn't where, this is just when. It happens at time 0. To find the where, we have to find the x and the y. So I'm plugging 0 in for t in my x formula, plugging 0 into my y formula, 0 cubed minus 3 times 0 equals 0, and 3 times 0 squared minus 9 is negative 9. So where does it have a horizontal tangent? At 0, negative 9. This is the point where it's going to have a horizontal tangent. We're going to check it here in a minute. Questions there? Okay, so let's talk about vertical tangents. What's it mean when the tangent line is vertical? What's the slope of a vertical line? Trick question. I hear everybody mumbling out, and let's say louder.
Maybe 0.
0 is flat, it's undefined, right? It's undefined if it's straight up and down. It has all rise but no run. It's undefined. When is a fraction undefined? When the denominator equals 0. So just like before, when we said the only thing we care about for horizontal is the numerator equaling 0, to find vertical, it's when the denominator equals 0. dy dx is undefined if 3t squared minus 3 equals 0. I'll write this up here. Sometimes I say it and I want to make sure it's clear. Well, just like over here, we said we wanted the slope to be 0 for horizontal. For a vertical tangent, we want the slope to be undefined. And a fraction is undefined if the denominator is equal to 0. Can we solve that? You can either solve it by factoring, or you can isolate the t squared. I don't know which way you prefer. I'd probably do this. 3 squared equals 3. Divide by 3 and get t squared equals 1. And of course, I would never forget that when I take the square root of both sides, there's a plus or minus.
3t squared minus 9.
Sorry, what'd you say?
Isn't it minus 9? 3t squared minus...
The derivative of
Oh, I wrote it down.
x.
Sorry.
Right, yeah, be careful, because y is 3t squared minus 9, but the 3t squared minus 3 was the derivative of x. They both had that 3t squared with a minus. I see the problem.
Yeah.
So what does that tell me? What's that tell me? It's going to be two different points. When t equals negative 1 and when t equals positive 1, there's 2 points where I'm going to have vertical tangent lines. So let's find those 2 points. So I'm going to plug negative 1 into my x and my y to find that point. So when I plug negative 1 in there for x, and I plug negative 1 in here for y, squared minus 9, I have to get it right. I think this one is a 2, and this is a negative 6. Doing arithmetic in my head, don't trust me. You're agreeing with me? Don't not just trust though, right? You guys are calculating it. So what's that tell me? 2 negative 6 is one of the points. 2 negative 6. And let's find the other one. Plug 1 into the x and y's. Three times, 3 cubed, 1 cubed minus 3 times 1, and 3 times 1 squared minus 9. I get negative 2, negative 6. So the answer is there's horizontal tangents at this only one point. There's only one horizontal tangent, and there are 2 questions up to there? So let's say this problem's on a test, and you want to check to make sure you did it right. I recommend graphing this curve and looking at it. So graph it on your calculator, we practiced that last time. Put your calculator in parametric mode and graph this function. Make sure your t's at least start somewhere before -1 and end after +1. So you graph that, and while you're doing that, I'm going to draw what I think it is up here. I think I did it earlier. But I want to make sure you can see it on your calculator. You could also plot points. It looks something like this. Ooh, I don't remember which direction it started. You guys will tell me if I can figure it out here.
First,
Yes.
what will we have with this?
Change your t values. Go into your window
Yep.
and have your t start at some negative number and go to a positive number. You got it now?
Yeah.
Anybody else having trouble getting that graph? What's the direction? Where did it start?
Top of it.
Started here? So it's this direction? I want to make sure everybody can get it. So now that you have that graph, are you still trying to get there? What point is this? Right here. -9. And look at the tangent line right there. What do you know? It's horizontal. Here's the point, 0, -9. There's a horizontal tangent right there, which makes me decide that maybe I'm okay over here. Guess what these 2 points are right here and right here. This one is 2, -6. And this one is -2, -6. So you've got the vertical tangents here, there's 2 of them, there's 1 horizontal. Do you see any other vertical or horizontals anywhere else? I've got some people shaking their heads. I don't see anywhere else where it would be vertical or horizontal, which means I didn't miss any either. So one way to check this work is to draw a quick picture of it and see, are those points where I actually see vertical or horizontal lines? And in this case, the answer is yes. Questions? Think you got this? Okay, so that's the end of 10.2. That's the end of 10.2. What we're going to do now is switch over to 10.3. Which is on page 99. I'll erase this board. We'll make sure everybody got what they need off the board here. We're good? Before I erase? Okay. 10.3 is kind of fun. For me. Hopefully for you too. I think the whole class is fun. It's going to start off really easy too. We always like things to start off easy, it makes us feel smart. Polar coordinates. So everything you've ever learned about graphing before polar coordinates has been in terms of ordered pairs, x and y. I give you an x, I give you a y, you can plot the point wherever it might be. I give you a graph, you can read the x and y's off the graph. What's going to happen now is certain functions, especially ones that have a lot of circles and loops in them, are easier to talk about in another form than talking about the x's and the y's. And what we do is we talk about polar coordinates. So there's 3 graphs across the top of your page, and they're all technically blank, but the background is a little different. So on the first one, I just want you to plot the point 1, 1. Maybe 2 squares could be 1, so it would fit on there. We all know how to find 1, 1? Yeah, we just go over to 1 and up to 1, right? It'd just be a point right there. What we're technically using is what some people call rectangular coordinates. Also called Cartesian coordinates. You probably heard that once and never saw it again, but now that we're introducing a new way of labeling things, you want to know if you're working in polar coordinates or Cartesian coordinates, which is the same as rectangular. But pretty much you'll hear Cartesian and polar. So you know how to plot the point 1, 1. So here's my question for you. On that next one, same point, let's put it in there again. Oops, evenly spaced would be nice. My question for you is, how far is it from the origin out to that point? Square root of 2? How'd you get that? Pythagorean theorem. So he's realizing that this distance is 1, and this distance is 1, and 1 squared plus 1 squared equals, we'll call it c squared for now if we're doing Pythagorean theorem. So c squared is 2, so c equals square root of 2. So this distance right here is square root of 2. So it's the same point. It's the same point 1, 1, but I'm interested in how far is it from the origin. My next question for you then is, what's this angle right in here? Theta?
45 degrees.
45 degrees? Or if we're working in radians, because calculus is always in radians, pi over 4. So this is what polar coordinates do. Instead of talking about tell me x and tell me y, it wants to know what's your distance from the origin, which we're going to call r, and what's your angle that you make with the x-axis. So polar coordinates are always going to be r and theta. So on your third graph, we're going to plot the same point, but we're going to look at it differently. If we're now in polar, and we have root 2 theta, root 2 pi over 4, which you guys just told me, right? Root 2 and pi over 4. The first thing I'm going to do is find pi over 4 from the x-axis. So I'm just going to find pi over 4, and it's this direction right here. Actually, it goes that way too. There's pi over 4. And then I want to go out a distance of square root of 2, which is approximately 1.4. So if this is 1 here and this is 1 here, this distance right here is square root of 2. And this is my pi over 4 angle. I still end up in the same point. Now some of you are going, I don't understand, why do we have to switch? I'm used to my x's and my y's. I can do x's and y's. Circles and anything that has different loops in it are so much easier in polar coordinates. What's the equation of a circle in x's and y's? Like the unit circle.
X squared plus y squared equals r squared.
X squared plus y squared equals r squared, but if it's the unit circle, then the radius is just 1. In polar coordinates, guess what the equation is? Here's a picture of it.
Sine squared.
What'd you say?
Would it be sine squared cosine squared?
That's actually where the relationship comes from the sines and cosines. But for example, this point right here, what's the r and what's the theta? How far am I from here? 1. And what's theta? 0. So if I was to make points, this is the point 1, 0. R and theta. What's this one right here? What'd you say? 1 and pi over 4? Right? Because I'm still going out 1, but the angle happens to be pi over 4. What's this one over here? 1 pi over 2. Can you see the pattern here? What's every single point gonna have?
One.
It's gonna have a 1 and any angle you want. The equation is r equals 1. There's no theta in it anywhere, because theta could be anything. You give me the angle, just go out 1, and you'll find a point on that circle. So here's an equation that's much nicer to work with than that. We'll be getting to these equations in a minute. Okay, so let's talk about how to plot points in polar coordinates. It's fine when we start off with things in the first quadrant, but then it gets a little bit weird. So let's do it over here. So my first examples, A through D, are just plotting points. And what's hard for some people to get with polar coordinates is there's more than one way to write them. Like there's only one way to write the point 1, 1. I'll go over 1 and up 1. But you know, theta keep repeating after a while, right? If theta equals 0 or theta equals 2 pi, it's the same place. So there's an infinite number of ways to write polar coordinates. So we're going to talk about that. So I'm going to first list these. A is 3 comma pi over 2. B is negative 1 pi over 3. Negative 2, 3 pi over 4. And 2, negative pi over 4. All right, so we're going to find all of these on here. What's my largest number? 3? So I'm just counting out the 3's on here since I don't have any r's bigger than that. So even though they're written with the r and then the theta, we start with the theta. So the first thing is, where's pi over 2? The y-axis going straight up. Right? Up here. This direction is pi over 2. So I need to look in that direction. So imagine you're standing here. You spin around so you're looking in that direction. And now you need to go 3 steps. 1, 2, 3. So this point right here is 3 pi over 2. Not so bad. That's the polar coordinates for it. What's the Cartesian coordinates for that one? 0, 3, right? Just x is 0, y is 3. Some of the Cartesians you can just read right off your graph. I didn't ask for the Cartesian in my example, but I like to tie those together, what you know and what you're learning here. So there's that one. This one's a little bit weird. Negative 1 pi over 3. So first I need to find where's pi over 3. It's in the first quadrant.
15 degree angle.
Did I say 50?
30.
30?
60.
One more guess. 60. If you can't remember, always just replace pi with 180. 180 over 3 is 60. So it's a little bit more than halfway. It's roughly here. It's roughly there. 2/3 of the way. So this is the direction of pi over 3. I'm looking in this direction. But what does this tell me to do? Negative 1. So imagine that I'm standing on the origin, I'm spinning around, I'm looking that way. If it says move negative 1, what's it want me to do? Go backwards. So you actually have to, oops, this one should be a straight line. I'm looking here, instead of stepping forward positive 1, I'm actually going back positive 1 to roughly right here. Because that direction is forward. So the forward and backwards is really weird for people. Instead of left and right, it's positive is in the direction of your angle, and negative is if you're stepping back away from that angle. So this point right here, which got really weird, is negative 1 pi over 3. Notice that even though pi over 3 is in the first quadrant, my point's not in the first quadrant. Questions on that one? People don't like those negative ones. You see why I step backwards? Okay. No questions? Let's do this one then. 3 pi over 4.
135 degrees.
You said 135?
Yes.
So yeah, that's over here looking this way, right through the middle. Here's 3 pi over 4. Remember I said when we get to chapter 10, you need to know your trig? Here we are. So if this is 3 pi over 4, but because this is negative, I need to go backwards again, so I have to continue this line down here. And instead of moving this direction, I'm going to move 2 steps behind me. So if I'm looking here, I'm going to go 2 back. And what I do to find 2 is if this is 2, I kind of just swing it over and estimate where it would be. Maybe right about here. I'm not going to point, measure it with my ruler. I'm not too worried. It's not all the way out to here. A little bit less than that. 3 pi over 4. Can you guys see the green? Oops. It seems really light to me. Can you guys read it? Yeah? I heard one yeah. Anybody say no? I feel like it would faint. Can you see Nick? Nick says no. Okay, I'm not doing any more green. I'll go over them with red. So there's those 3. And the last one is 2 negative pi over 4.
315 degrees.
It coincides with 315, but negative pi over 4 means what when your angle's negative? You start off going down, and look at the hand thing, we'll just start off going down pi over 4. So this angle right to here is my negative pi over 4, so I'm looking this way. And then what do I want to do if I'm looking that way? Go out a distance of 2. Where do I end up? Same place. This point right here, which was negative 2, 3 pi over 4, is also positive 2, negative pi over 4. It's both. Remember I said there's an infinite number of ways that you can write each point? Yes, ma'am.
When you're going backwards, when it says -2, are you going like 2 spaces using the y-axis or the?
Good question. So that's why I said I kind of swing it around. So you're talking about when I found this point the first time. So this distance right here is 2. So what I do is I kind of rotate it around and say, what if I was going over here? Because you can't go 2 in the y direction because that's too far, right? So yeah, you just kind of have to estimate. If this is 2 and you spun it around, it would be, maybe over there. It wouldn't be as far out as 2 and 2. So it's actually 2, is assuming this scale here was the same. Right, you have to have a little scale on that one. Yes, go ahead.
Could you
Emily.
do where you know how r equals 2, that means when x equals 2 and then y equals 2 and then kind of draw a circle kind of like thing, and then do the point right there, if that makes sense.
So I think that's what you're saying. You're saying take 2 and 2 and do a circle like this?
And then yeah, do a point.
Exactly. So that's what I was saying when I kind of take this and swing it around, where would it hit?
Oh.
Because it's not 2 and 2, which would be over here. It should be that same distance though. That's a good way to look at it. Yeah, Zach?
Would positive 2 and 315 degrees be the same point as well?
Let's find out. 2 and 315
That's
degrees, that's 7 pi over 4.
Yeah.
I stay in radians. So his question is, would 2 and 7 pi over 4 be the same point? I have 2 people nodding. 7 pi over 4. Here's the way to easily find 7 pi over 4, by the way. Here's 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7 pi over 4. So if you can't tell where 7 pi over 4 is, just count by pi over 4s till you get 7 of them. Because you guys know how much pi over 4 is. So 7 pi over 4 and 2. So there's 3 different ways right there to say the same point. Yes?
Is there a trick where you just add like 8 pi over 4?
Yeah.
It's just-
So he says just add 8 pi over 4. Or you could subtract 8 pi over 4. Because what's 8 pi over 4?
2 pi.
2 pi.
I just find this one.
So we could add 8 pi over 4 to this, we could add 8 pi over 4 to that. If you add it to this one, it gives you this one.
Oh, I meant like a trig, because a lot of people like try to figure out what quadrant it's in, but 7 pi over 4 is just one less.
Right, one less than
Right,
8.
so if I'm at 2 pi minus 1, it's just.
Yeah, so that's exactly how I find it. So instead of counting to 7 like I just showed you, I think, well, let's see, 2 pi is 8 pi over 4. I'm just one less than that, so I'm going back one. So I do the same thing, I think, do I need to go forward or backwards from either pi or 0 or 2 pi? Mhm. However you see it, I like it, as long as it's correct. Other questions? Okay, so my next question for you is, so this point we just beat to death, we gave it 3 different polar coordinate names. What is it in rectangular coordinates? What is this point right here in rectangular? We gave it 3 polar names. Another color, how many other colors? Change lids on my pens too, now I'm confused. What is this in rectangular? How would I find it? What'd you say?
Triangle.
A triangle. We know the hypotenuse is 2. And we're looking for this distance and this distance if the hypotenuse is 2. It's a right triangle. And what are these angles? 45. Angle, side angle. How are we going to find those? What do we know about these two sides? They're the same. Call them A, maybe we call it, I don't know, A, and this one would also be A, right? Because they're the same. A squared plus A squared has to equal 2 squared. 2A squared has to equal 4. A squared equals 2. That one. What's A? A equals square root of 2. Now, be careful. What point is that? In rectangular coordinates, Cartesian. Root 2? There's something missing there.
Negative.
The second one's negative. Because we went down, right? Over root 2, down root 2.
So what about the other one?
What about the other ones?
Yeah.
Okay, I like it. He's like, he must like this. He wants me to do more than I've asked on my notes. This is good. We're going to talk about how to convert all of them. Questions on that one though? So before we switch some of the other ones, what I want is some other polar answers for this one. So this is polar right here, right? Can you give me another way to define that in terms of polar? Like maybe with a positive R and then an angle?
1 3 pi over,
Too close. I'll wait.
5 pi over 4.
Well, this is a pi over 3 to begin with.
Negative 4 pi over 6.
Nope. It's going to have to be multiples of pi over 3. 4 pi over 3 would work. Because this was a pi over 3 here, this is still a pi over 3 over here. So how he got 4 pi over 3 is this is 1, 2, 3, 4 pi over 3. Or you think of it as pi plus another pi over 3, however you want to look at it. But because this was pi over 3, anything you add or subtract to it will still be have the over 3 in it. That doesn't change. What about if we had a negative angle?
1 negative 2 pi.
1 negative 2 pi over 3? Right, because this would be negative pi. Go back one more. Negative 2 pi over 3. Again, it's all about how well you know your trig. And we could do this all day long. There's an infinite number. The reason I'm finding a bunch of them is when you're working on your assignments, on your lab assignment or on your web assign, it'll tell you to find the polar coordinates and say, I want R to be positive, or I want theta to be negative, or I want both of them to be negative. So you'll have to mess around with it to follow whatever restrictions you're given. So it was given to us with a negative R and a positive theta, but we could do it with both positive, we could do it with one positive, one negative. We could make them both negative if we wanted. questions there? This one's kind of boring. Can you give me this one with a negative R? What about this one with a negative R? This one right here.
Negative 3 pi over 2.
Negative 3 pi over 2, he says. Let's see if he's right. 3 pi over 2 is 1, 2, 3 pi over 2. It's looking this way. So if I'm looking this way, I need to go backwards by 3, so I'm going to go back 1, 2, 3.
Only one.
So that works. What'd you say, Joseph?
Oh, I was just thinking of that. I was like, yeah, because only one has to be negative.
Right. Can we do it with both negative, the r and the theta? What angle? So if r has to be negative, I have to be looking down here, right?
Negative 3, negative 5 is square root.
Oh, yes, beautiful. Negative 3, negative pi over 2. Right, go to negative pi over 2, you're looking down, and then go backwards up 3. We beat this one up pretty good. This one was already given to us in 2 forms, we can't do that one again. So then the question becomes, okay, this one was pretty easy to switch to Cartesian. This one was a little bit messier to switch to Cartesian. What about these other ones, right? Like this one over here, like how do you switch that to Cartesian? Not quite so obvious. That's where we're going next. Don't answer that, but that's the question, and that's what we're going to talk about next. You don't need to answer it right now. Okay, so let's talk about how to convert between them. We got time for setting up our conversions. So in general, you have some x, some y, and some r. Right, that's what we were doing, x and y, and the r was the distance from the origin. And this was our theta. And then over here in this box, you're going to fill in these formulas, and you will memorize these very soon if you don't already know them. And we're going to start wherever we want. So the first question I have for you is, I think you know this one. What's x squared plus y squared equal to? R squared, that's just Pythagorean theorem, right? Piece of cake. What about this one? Tangent of theta. Y over x, opposite over adjacent. I learned it as the actual y over the x, however you learned your trig. Those two are just from what we know already. Now this one, it's not clear where I'm going with it, but it has to do with how x is related to r and theta. So what can you tell me, using your trig knowledge, about theta and x and r? Which trig function relates x and r? Cosine, right? Cosine of theta is x over r. So what's x equal to? R cosine theta. And what's y equal to? R sine theta. So technically, none of that's new, right? It's all stuff you learned in trig or algebra. So if you forget the definitions, draw a little triangle and ask yourself, what's the relationship there? And you'll be able to find that. So this is how we can switch from one to the other. So when Daniel says, well, what if we want to switch this one into polar coordinates? From polar into Cartesian. You just stretching, Lila?
Yes.
Okay. We're going to finish this one and then you'll take a break. So let's say we had that negative 1, what was it, pi over 3? So we had this one right here. When we look at it, what do you know about the x's and y's? And if you were guessing what they were? What would you guess they are? Positive, negative? X is negative, and y is negative, right? Because it's down here in the third point. We know that much. You think they're more or less than 1? They're both less than 1, right? Because go over a little bit and then down not quite 1. So I should get 2 negative values that are kind of small. So if I want to find what they are for x's and y's, this is my r, this is my theta, I can just plug them into these formulas. The x is equal to -1 times the cosine of pi over 3. Which, hopefully you know your trig. Cosine of pi over 3 is 1/2. So it's -1/2. The y is the r times the sine of pi over 3. Sine of pi over 3 is √3 over 2. Negative √3 over 2. So the Cartesian coordinates for this guy is
-1/2 square root 0.2.
perfect. -1/2 minus √3 over 2. That's roughly 0.5. This is like 0.7 or 0.8, I think 0.8. So over a half down 0.8, roughly there. When you're converting, you're always going to want exact answers for your Cartesian, so you don't want to put decimals. Sometimes I change them to decimals to plot them, because it's easier to find 0.8 than to count by square root of 3. But you're going to want to leave the exact answers for this. So after our break, we'll do this other one that's asking us to convert it. And then here's my challenge for you. Can you find a point that has the same answers for Cartesian and polar? The same ordered pair for Cartesian and polar. That's my challenge for you. Think about it over the break. You write down what I'm saying? Same pair for polar and Cartesian. Okay, that will work. But maybe I want a more interesting one. You already found one. So let's take a break. We'll come back and we'll do some more polar coordinates. Polar coordinates. Polar coordinates continued. Did anybody come up with the same ordered pair?
1, 0.
1, 0, he says? If r equals 1 and theta equals 0, is that the same as x equals 1 and y equals 0? Question mark? So theta equals 0 means I'm looking in this direction. I'm going to go out 1, so I'm here. It's also x equals 1, y equals 0. So yeah, that's a good one. Somebody come up with a different one?
0, 1.
0, 1? 0, 1 doesn't work.
No?
First off, 1 radian,
Oh.
it's like, I don't know how to figure out what 1 radian is. I'd have to figure out what that is in terms of pi over what. It's like somewhere in, 1 radian is like somewhere in here. This angle, I don't know where exactly, roughly here maybe? We'd have to convert, because that's 1, which is what angle, right? And then I'd have to go out a distance of 1, which would be putting me up here. So because that's radians, that's why it doesn't work. So it has to be, the theta would have to be the 0, not the, oh, 0, 1. I take that back. You're fine.
I was just thinking about the y.
I was thinking of the angle. So the angle is all wrong. It doesn't really matter though, because no matter what direction you're going, you're going to end up with 0. So you're right. I'm sorry. I take it back. See what I mean? I was worried about your angle, but it really doesn't matter because you're not going anywhere. So 0, 1 works also. Anything else? Anybody else try it? An ordered pair that's the same whether it's polar or Cartesian. Do I do one with like a negative?
-1, 0.
How about something that's not a 1?
What about something with pi over 4?
Okay, so if you want a pi over 4 in here, oh, I took yours back. Wait, I have to go back and take yours back again. I just realized. 0, 1's not right. Darn it. It's okay. Pi over 4, We can't come up with anything that's gonna work. Here's why. Even if you put a 0, that's why I realized that your other one was technically wrong. Let's go back up. Because if I'm looking in this direction and going out of distance of 0, I'm at this point right here. This is 0, 1 polar. What is that Cartesian?
0, 0.
0, 0. Darn it, that one didn't work. I knew I was right. Almost gave you credit for that. Same problem here. As soon as you're looking at pi over 4, okay, you're saying your y is pi over 4?
Mhm.
So if your y has to be pi over 4, you probably could figure out what that distance is, figure out, but then as soon as you change your x, it messes all up. So again, I can't figure out what you would put here that would work. So that one's actually gone too. I think the only ones that work are when you have a 0 here. Why? Why does it work if it's a 0 here? If theta equals 0, where are you? If theta equals 0.
On the x-axis?
On the x-axis. And if you're on the x-axis, your y is also 0. As soon as you need to move off of it, you're out of luck. But you could do other numbers, like, 17, 0 would work. -3 million, 0 would work. You'd have to have that 0. Let's just think about it. Okay, let's go back to our notes though. We had just discussed these formulas, and the question is to convert 6 2 pi over 3 into polar. Excuse me. Yeah, convert 6 into Cartesian. Six 2 pi over 3. We want to convert that to Cartesian. What are we going to do? How are we going to convert that to Cartesian? It's not an obvious one like those. What do I need for Cartesian?
You do it with a triangle.
I do it with a triangle. But in general, when I list Cartesian coordinates, instead of r and theta, what do I need? X and y. If I need x and y, we could draw a triangle, but we also could just use these formulas that come from any generic triangle. That's why we did this before. I just need to find x and find y. Plug it in. X equals 6 times cosine of 2 pi over 3. And y equals 6 times sine of 2 pi over 3. Need to be careful. 2 pi over 3 is in the second quadrant. So what's the cosine?
Negative 1.
-1/2. Remember I said you gotta know your trig by today?
And second one's root 3 over 2.
And the other one is root 3 over 2. This ends up being -3, 3 root 3. Okay with that? Let's plot that to see if it makes sense. What's my answer? Yeah, an ordered pair, make sure we finish that. Oops, this one's positive. Let's plot that, that's xy. So -3 means I'm going 3 to the left. What's 3 root 3 is a decimal? Someone help me out there? 3 times square root of 3? Say again, I couldn't hear you.
5.19.
5.2-ish. 1, 2, 3, 4, 5.2. I'm gonna go over -3 and up about 5.2. Puts me right here, roughly. I just plotted this point. I went over -3 and up 5.2. So when I'm trying to plot them, I change them into decimals so I can find them. And then, oops, I missed. If we look at that angle, does this angle look to be about 2 pi over 3? And this distance looks to be about 6. So we took this polar and changed it to Cartesian. You don't always have to plot it, but I'd like to. I at least like to check the signs to make sure I'm in the right quadrant. You all right there? Okay, so the next example has us going backwards. Converting Cartesian into polar. Converting Cartesian into polar. I'll leave my little box here because I'm going to need it. -1, convert to polar. By the way, there's multiple answers. Remember how little polar, we could list a bunch of different ones? So if this was on an exam, I might ask you to convert it to polar, but I want r to be negative, or I want theta to be negative, or I want them both to be positive, whatever. But we'll just convert it first. Where do you think we should start?
Graph it on our resume.
We could graph it. I like to graph it because that gives me a visual of whether or not my answer makes sense. Well, we'll graph -1, -1. Here it is. Solve for r. Because if you're converting to polar, you need r and you need theta. How can I solve for r? Pythagorean theorem, which happens to also be right here. Right, those formulas are there for a reason, so I'm going to use this formula, which is the Pythagorean theorem. -1 squared plus -1 squared equals r squared. So 2 equals r squared, r equals square root of 2. Does that surprise anyone? I heard one person say no. Why is it not surprising? It's a 45, 45. 1, 1, square root of 2 is a relationship for that triangle, special triangle. So r equals square root of 2. Technically, r equals plus or minus depending on which angle we use. Right? It could be a positive r, it could be a negative r, we don't know. So we have r. We also need theta. Now, we just talked about that we knew it was 45 degrees. But what if it wasn't 45 degrees? What if you couldn't tell? Like if it was at -7, -8, not a nice angle that I know. Let's just make sure that besides recognizing it, how we could find the angle.
Tangent theta equals y over x.
Exactly. So in this case, we're going to use that. We could have done it without it, but even if x had been 7 and y had been 8, we could have used this formula that the tangent of theta is y over x. So in this case, it's -1 over -1. So the tangent is 1. So now you need to know your trig. Which angles have a tangent of 1? Theta could be angle has a tangent of 1. 45 degrees, which of course I'm going to change into radians. Pi over 4. 4. 5 pi over 4. There's another one. 3 pi over 4. There's an infinite number of them. All these odd multiples of pi over 4 would work. Are you using your hand signals or are you raising your hand?
Oh,
You're thinking, okay, you're thinking with your hands, I like it. All right, so there's lots of thetas. We could find them. Let's list a couple different, yes ma'am?
Can you also just take the inverse of tan of 1?
Yeah, so if you did the inverse tan of 1, which would be perfect, by the way, if it was like 7 over 8 and we don't recognize it, the inverse tan of 1 will be pi over 4. So the problem with inverse tan is it only gives you one answer, and then you'd have to figure out which other quadrants, which you could just add pi over 2 or add pi or 2 pi, whatever you might need to. But yeah, so because I think there's one problem on the lab where this is not a nice number, and you would just use the inverse tan to find the angle. Okay, so now what? convert it to polar. Give me a polar pair for this one, an R and a theta.
Square root of 2, so 5 pi.
5 pi over 4? Nope. Oh, 5 pi over 4, yep, sorry. I thought, thinking another one, sorry, I was thinking 7. I'm like, wait a minute. 5 pi over 4. Because 5 pi over 4 is right here looking this way. And we want to go exactly square root of 2 in that direction. What's another option?
Negative root 2 pi over 4.
Negative root 2, positive pi over 4. That means we're looking in this direction. But if we're looking in that direction, we're going to go backwards, so that would put us down here. So these are like the problems on the lab where I'll ask you to convert it, but sometimes I'll give you restrictions. What if I want a negative angle?
You could do
Root 2 negative 3 pi.
Ooh, I like it. Root 2 negative 3 pi over 4. So you could do positives, you could do one of each.
You could do negative root 2, and you do 5, negative 1.
Yeah, we could do negative root 2 and negative 5 pi over 4? Not 5 pi over 4. 7 pi over 4. If you wanted them both to be negative, we would have to go all the way around almost to 2 pi. Let's put it back up a little bit, right? 7 pi over 4. That would work too. That's all, making sure we got our trig down. So when you're switching from polar to Cartesian, you can just find x and y just by doing this every time. When you're switching from Cartesian to polar, this will help you get your angle and your r, which are all just our trig information. All right, so now that we can change points from one to the other, we want to change entire equations. Like remember earlier I told you x squared plus y squared equals 1 was the same as r equals 1. Every point on this circle also has an r value of 1 if you change it to polar coordinates. So we're going to take entire equations and change them into polar equations, or vice versa. So my first one is, what do you think r equals 4 represents? A radius of 4. What's theta? There's no theta in that equation. Could be on the axis. But what does theta have to be? What does it tell me about theta? Trick question. What's it tell me about theta? Nothing, which means theta can be anything I want, and this will still be true as long as I go out a distance of 4 from the origin. So I can go with theta equals 0 and go out 4, or I can go pi over 4 and go out 4, or I can go here and go out 4. As long as I'm going 4 away from the origin, all these points are 4 away from the origin, and it doesn't matter what angle. You could look at any direction you want and just go a distance of 4. So this is a circle of radius 4. It's like so easy, it's hard. And a lot of people are like, well, but there's no theta. You guys already know how to graph equations like don't have x's and y's. Like, can you graph y equals 5? What is that? That's a line? What kind of line?
Horizontal line.
It's a horizontal line where the y is always 5 and what's x? Anything, right? Any x you want as long as you go up 5. The same kind of idea. Any theta you want as long as you go out 4. Okay. So then the next part says, what if I put some restrictions on this? What if I change it to the absolute value of r is less than or equal to 4, and theta has to be between pi and 2 pi. So let's do this part first. If I'm between pi and 2 pi, where am I? Anything below the x-axis or the third and fourth quadrant. So that means I'm only looking at angles, I'm going to have them draw them in here. All these angles in here, looking out this way, right? All these angles. I'm looking in any of those directions. And then my r, the absolute value of r, has to be less than or equal to 4. What does that mean?
Anything
As large as that half circle or smaller?
Uh-huh, as large as that circle or smaller. So if I'm looking, say, in this first direction here, this one, I can go out 4 if I want, but I can go out 2. Or I can go out 3, or I can go out, I mean, any point in here would be an R less than 4. So it pretty much shades in all of this. This is colored in so beautifully too. Every point in there has an R that's less than or equal to 4. Because R equals 0 is just sitting right there. If you go any distance, just can't go past that line. But I claim this isn't the whole thing. Part of it we've ignored. It's not the whole answer. I claim that this point over here is okay. Ooh, the silence, you can feel it? Because R could be negative, and as long as I take its absolute value and it's less than 4, R could be negative, right? So say this point right here is, let's just label it. Let's say it's, I'll put my theta first, sorry. Say it's -2, well, maybe it's -3, and it's, what would that be? 5 pi over 3, roughly. So 5 pi over 3 is over here. Negative puts me back up there, roughly. Does that satisfy this? Is the absolute value of R less than or equal to 4? It is. And the angle is between pi and 2 pi. So even though this makes it look like you have to stay in the 3rd and 4th quadrant, because this is absolute value, I could have negative R's too, so it's actually the whole circle colored in. Any point inside the circle, including the edges. This is a beautiful picture. People in the video are going to love it. Everything inside there. If this hadn't had the absolute values on it, then it would have just been the lower half. Because you would have had to have your R as positive, right? But the absolute values led us to the top half as well. Okay, so let's look at example 3, a much messier equation, not as straightforward as a circle. R equals -8 cosine theta. R equals -8 cosine theta, and we want to convert to Cartesian. All of a sudden it got hard. Well, I didn't write the Cartesian for that one over there, did I? I see my question on the notes asked us to. What was the Cartesian equation for this guy? The original one, the outside? Cartesian equation with x's and y's. What's the equation? If R equals 4, the Cartesian equation is equation of a circle with radius 4. You knew this before you learned polar.
X squared plus y squared equals 4?
Close. X squared plus y squared equals 4 squared. Right? R squared, R squared. So the equation was x squared plus y squared equals 16. Cartesian equations for circles are a lot messier than polar equations for circles. I just realized I asked it and didn't do it. Circle with radius 4. Okay, let's go back to this one now. Okay, converting to Cartesian, meaning change everything into x's and y's. This is all we know. How are we going to use that to convert this into an x or a y? That's the question. I'll take some thoughts. Things that you wish you had there, things that you think you need to do, things that you don't like about it.
Could you pull up the -8
Pull out the -8.
to the front and then switch with the R?
Well, I can't switch them because, I mean, I can divide by it. If I switch them, it would change the equation. Yeah, Zach?
Can we plug the R in for the R cosine theta and the R sine theta?
So if I had r times cosine theta, then I could replace it with x. Is that what you're saying?
Yeah, I just meant the -8 cosine theta times cosine theta and -8 cosine theta times sine theta, if that's what R equals.
So let me see what you're trying to say. So you're saying take this equation
We're gonna for
that tells you, and then plug in,
For R,
okay, I could do that. -8 cosine theta is r, cosine theta. And then times this other cosine theta. So you guys see what he's saying? This r right here is the r. The problem is I still have cosines in here. X equals -8 cosine squared theta. We're getting somewhere though, but instead of r's and theta, we just have thetas. You want to do it with the y's also? Is that what you were suggesting?
yeah.
Okay, let's try it. So we plug in the r. So y equals -8 cosine theta sine theta. So we got rid of the r's, but now we still have thetas. You see the problem? Like, now what? Good plan. If one would have been cosine squared and one would have been sine squared, then we could maybe use an identity. But I'm not so sure it's getting me anywhere. Because I can't see the relationship between x and y. Remember what we know about how to get x's and y's. We know that x is r times cosine theta, and we know y is r times sine theta. So I'm going to go back to the original one again. See another plan. I put a space there on purpose. Wouldn't it be really nice if there was an r right here? Why? Why would that be nice? You don't know? Don't you think? I don't want to divide it out. Who cares what's over here? It might be something else over here. But if I had an r right there, I claim that would help me a lot. Why?
see what that.
Because that's just x, right? R cosine theta is x. This right here is x. The whole goal is looking for r cosine thetas. Well, that r is not there. I just stuck it in there. I multiplied that side of the equation by r. So I have to multiply this side by r. So I can stick it in there. I wish it was there, so I'm going to put it there. But just like we learned in algebra, if I multiply it on this side, I better multiply it on that side. So now I have r squared equals 8r cosine theta. I lost the negative. I dropped it. And I put it back. Thank you. I dropped it.
Oh, but then we have r squared is with x squared plus y squared.
Mhm. So he sees two things. This right here is our definition for x. But this is x squared plus y squared. So when you're trying to convert from polar to Cartesian, you're looking for either r cosine theta or r sine theta, or if you're lucky, an r squared. Because those are all the things that can relate it for you, or get tangents as well. So what's this equation become now?
X squared plus y squared is equal to -8x.
X squared plus y squared equals -8x. We've just converted it. This is a Cartesian equation. You could leave it like that. But my next question is going to be, what's that an equation of? I'm going to rearrange it to answer that question. That the same equation? You guys know how to complete the square? If I want to write this as a perfect square, it's going to be x plus half of this. Half of this is 4. But if I square that 4, what am I going to get? 16. So I need to have a 16 right here to make this part equal this part. Okay? But I just added 16 to this side of the equation. So I'm going to add it to the other side of the equation. now I have this. Anybody recognize it now? It's a circle. With what radius? Radius 4. Where's the center of this circle? Negative 4, 0. Yeah, I got moved 4 to the left. Center at negative 4, 0. If you put the original equation into your calculator and ask it to graph it, I haven't told you that yet. Your calculator can graph in polar coordinates too. We need to do that right now. So remember last time we talked about how to do it in parametric? There's also a polar mode. Let's sketch the graph of this on our calculators. First go into your mode, change it to polar. Type in that equation. Most likely it won't look like a circle, and I'll tell you why.
You plug in the R, getting that,
Yeah, you have to solve for R. Yes, you just, it's already this. You just
Yeah,
plug
so
this
you-
in there and then graph it.
but it comes out as a circle.
It looks more like an ellipse.
Yeah, it should look like an ellipse. But there's a way to fix it.
Oh, yeah.
Yeah, the Zoom is gonna do it. But let's see, it should look like an ellipse, and I'll talk about why in a second here. See if you can graph it. You don't need all this. How did I know? Just put that R in there. I just did it. You're like, oh, now I see it. How did I know to stick this R right in here? Besides the fact that I've been doing calculus for 40 years. What tells me I want that R there? What'd you say? Yeah, the equations. I'm trying to find an X and a Y in there somewhere. And I need an X, a Y, or an X squared plus Y squared, or an R squared. And if I don't have any of that, I need to mess around until I can get them, yes.
You just insert a bar and that's it.
As long as I do it to both sides. So whatever you do on one side, you can do it to the other. Sometimes you'll divide by the same thing on both sides. You can multiply by something else. It all kind of depends on what you're working with. I lost my notes. Oh, they're over here. Okay, so let's talk about the next one. Now we have a line, 5x minus 3y equals 15. So this is example 4. 5x minus 3y equals 15. Equation of the line, we want to convert that into polar. I want to change it so it has r's and thetas in it. Instead of x's and y's. I just erased my formulas, darn it, I can't point to them.
Couldn't you square both sides?
I could square both sides, that might give me a mess though, what'd you say?
X squared, Y squared.
I don't have x squared and y squared though. I don't even need to solve for individual variables, I'm just trying to get rid of all my x's and y's and change them to r's and
Just
thetas.
replace it with this.
Yeah, just replace it with the definitions. X equals r, I can't point to it. X equals r cosine theta, y equals r sine theta, just stick them in there. The x is r cosine theta, and the y is r sine theta. Just stick it in there. Whatever formula you have. I just erased mine, I should have not done that. That's my x and that's my y, okay? If I want to put that in my calculator though, I'm out of luck, put it in that way. This is a a polar equation. Solve for r, we can solve for r. What can we do to solve for r? Factor it out. R times 5 cosine theta minus 3 sine theta equals 15. So r equals 15 divided by that mess. Do me a favor and put that one in your calculator carefully. See if you get an equation of the line. Make sure you got the right denominator, right parentheses. equation of a line? So, that's a really messy equation of a line. Here's our polar, this was our Cartesian. Why is it so messy? What is polar doing for us? Look over here, we had, this was our polar, whoops. This was our polar, and this was our Cartesian. That one's a lot messier than this one. Polar does what? So what's the advantage of polar coordinates?
Different variables?
Yeah, they're different variables, but why are they better or worse in some situations? What is it measuring? When you have r and theta, all we care about is what?
The angle and the radius?
Yeah, an angle and a radius, an angle and how far you are from there. So when you have a graph of a line, like every angle is different and every radius is different. There's like no pattern to this in terms of anything that might be circular, or the radius might be the same, or the angles might be the same. So when you're working with Cartesian functions that are not circular in some form, you'll see more later on about the other forms. You're gonna see pretty flowers pretty soon, things that do this and like that. I can't draw them, but things like that, where they rotate around on themselves. Anything that rotates around, you're gonna want polar, it's gonna be nicer. Anything that has straight lines, you're gonna want Cartesian. So that's why in this case, the polar for the circle was actually fairly short and sweet compared to this over here, but for a line, the other way around worked better. Questions there? Okay, underneath that example in your notes, are a list of all kinds of different shapes that we're going to be seeing. I'm going to talk about some of them, not all of them. Number one, it says lines. It actually should say lines through the origin, because here's a line that doesn't satisfy that. And I'll tell you why in a second. Lines through the origin. Is theta equal to a constant? So this says theta equals any angle you want. So maybe I choose theta equals pi over 6. I claim that that's the equation of a line through the origin. Let's talk about why. Can you give me some polar coordinates, some r and thetas that go with that? Give me some ordered pairs.
3 and 5 or 6.
3 and pi over 6. I like that one. Anything else? Just want you guys to make some up for me.
-7, 5 over 6.
-7 and pi over 6? Because there's only one who can make these up? 2, is that what you said? 2? I need a data.
Oh, 5 or 6.
Oh, better be pi over 6. Okay, good. Just making sure we all got that. So this equation just says make sure that theta is pi over 6. R could be anything. R could be 0. R could be -100, as long as I've got pi over 6. Right? All day long. I can't put that into my calculator because it's R equals, right? So let's talk about this. Pi over 6 is looking in this direction. 30 degrees roughly. So I could go out here a distance of 3. Let's make that 3 right here. What do I do for -7? I would have to go down this way, right? Go backwards. -7 would be out here somewhere. +2 would maybe be over here. 0 is right there. -100 is down there somewhere. I can't get to there. Do you agree that no matter how far out you go, you're going to be staying on this line? Any point out this direction, any point out this direction, is on that line where theta equals pi over 6. That's a line through the origin. But anytime theta is a constant, you're just going to have that nice little line. It only works nicely for through the origin. We saw how messy it is if it doesn't go through the origin. Through the origin is pretty. And then there's vertical lines and horizontal lines, which should look pretty straightforward, because if r cosine theta equals a constant, that says that x equals a constant, and vice versa, y equals a constant. So those are pretty straightforward. Circles, we already talked about. There's an example of one like this. Some constant times cosine. There's r equals 4, like we did over there originally. What do you think would happen? This was the circle that was off to the left. It looked like this, roughly, this guy. What do you think would happen if you put a sine instead of a cosine? What do you think that would do to the graph?
Move the circle to the top half.
Yeah, move the circle either to the top or the bottom, depending on your r, if it's negative or positive. Basically, they're going to end up right or left, depending on if it's negative or positive, and a cosine. And if it's a sine, it'll go up or down. Same reasoning as this problem here. Just kind of shifts your circles around. So there's 3 types of circles. They just get shifted left, right, up, down, or stay at the center. And then there's these cool things called cardioids, limicons, and roses. Cardioids actually have, we're going to grab some of these coming up. See a lot of them next time after spring break. Cardioids actually kind of look like a heart. Like they'll do something like that when you graph them. They'll have like this little lump on them. We'll talk about how to recognize when you have a cardioid. And I have the equations written there. I'm never going to ask you to memorize which ones are which. I just want you to know these are shapes that you're going to be seeing. A limicon is the same idea as a cardioid, except instead of stopping, it kind of makes a little loop inside there. It actually loops back inside itself and comes back out. And they can be sideways too. You can have one that does this. It goes sideways, things like that. Which are limicons. And roses are like the thing I attempted to draw a minute ago that was really bad. Roses can have any number of petals. They can have 3 petals. They can have 4 petals, right? 5, 6, 8, whatever. 16, whatever. And we'll see those as we start going. So these are the kind of things that we're going to be graphing with poles. Oh, we're almost out of time. Okay. In the interest of time, I'm going to shortcut that last little bit. So remember last time with parametric equations, we did dy dt over dx dt. When we wanted dy dx for parametric, we did dy dx, dy dt over dx dt. So now we want to do the same thing, but with respect to theta. We want dy d theta over dx d theta. But, let me write this up here. Remember that y equals r sine theta and x equals r cosine theta. So when you want to take the derivative of y with respect to theta, you actually have to use the product rule, because r is a function of theta also. You actually have to use the product rule here, and you have to use the product rule there. Messy, I know. So I could derive the whole thing for you, but instead, I'm going to shortcut and write it up here for you, and you can look at the product rule later. There's the derivative of the first times the second, plus the first one times the derivative of the second. That's the product rule on this guy. And the product rule on the other one, minus r sine theta. Where did minus come from, you think? Down here.
Derivative of cosine.
Ah, derivative of cosine is negative sine. That's where that comes from. So this is how you're gonna find the slope of the tangent line for anything that's in polar. You do not have to memorize this formula. You do not have to, I will give it to you. So if I ask for an equation of a tangent line, you just have to plug all that stuff in there. It's similar to what we were doing. So that last example, example 5, says r equals 3 plus 8 sine theta, and at theta equals pi over 6, it wants us to find the equation of the tangent line. What would I do? A lot of thetas and r's and messes up there. What would I do to find the equation of the tangent line? What do you need to find the equation of any line?
Point and a slope.
A point and a slope. Let's talk about how we get the point. I need a point, which would be an xy. How am I going to find xy?
Using
Yeah, using these right here. I have theta, they gave it to me. What am I gonna plug in for r?
Just solve for r.
Yeah, we can plug theta in here also, right? We can plug pi over 6 in here and get r. And then we plug the r times the sine of theta and r times the cosine to get our x's and our y's. Right? How would we get the slope?
derivative.
The derivative. We would have to plug those r's and those thetas into here. How fun, I like the attitude. What's dr d theta? What is dr d theta? What's that mean? Derivative of this with respect to theta. And we'll plug theta in there as well. So I don't have enough time. We're out of time for me to finish this problem, but I think we can do it. We're just plugging everything we have into there. The answer, if you want to try it, should be 11 square root 3 over 5x minus 48 over 5. I will be in the lab today from now until 4:15. I'm in my office later tonight from 5 to 6:30. If you want to work on this before spring break to get it done, try that one. I think you should be able to do it though. I'll see you.